Yeah, it was muted. Okay. Okay, let's continue on the physical properties of asteroid surfaces, and now I think we'll have a more theory, computationally oriented session where we drill into the actual modeling of the particulate medium with inhomogeneous small particles. So yesterday this was an introduction to asteroid UV-Vis near-infrared spectrometry, and today it's entitled Novel Spectrometric Modeling, but at the same time this also involves photometric and polarimetric modeling. And basically the idea is to certify using polarimetric and photometric modeling that actually we can truly compute scattering from a particulate medium in such a way that it compares in an acceptable way with the exact electromagnetic computations based on the Maxwell equations. So let's see how we can potentially do that. So the contents today is roughly some introduction there, then multiple scattering. I'll talk about the radiative transfer and coherent backscattering, defining what that is on the way, and this is RTCP. Then we go into RTCP with incoherent fields. You will learn later what incoherent fields actually mean in this way, in this case. Then radiative transfer with reciprocal transactions, which is our abbreviation R2T2, not R2D2, but R2T2, just to remember this in the future. It is essentially a new kind of radiative transfer approach that is based on more or less exact computations in an order of scattering fashion in a regolith of small particles there. Some preliminary results to convince, first of all, I guess, us and you that there may be something interesting in these methods, that actually they can succeed in doing the computation correctly. Then spectrometry revisited. We look at the space weathering. We look at the Chelyabinsk meteorite spectral modeling, and then, as promised yesterday, I will actually define a spectrometric inverse problem for anybody interested in playing a little with an analytical tool to invert some simulated spectra I expect. One can actually also introduce real spectra, but I'm thinking of here a fully computational approach where the actual input spectrum is also simulated with one code, and then one uses another method to invert, and one can then actually compare how well the codes work, how consistent is the treatment. So the introduction is the same as yesterday, so it's green now. Yesterday I had blue colors, green colors today. I repeat the same slide here, so you don't need to read that. If we have basically the direct problem and the inverse problem, and we are interested in the fundamental properties, size, shape of particles, refractive index, or optical constants, and we try to derive them from observations, measurements. And we have the structure here, the basic definitions on the board, blackboard, for phase angle, and then light source, asteroid, observer, and then the plane of scattering, and the polarization also defined here. So you can see that we use exactly the same definition now in the modeling purposes. So what you will see is potentially something not as a function of necessarily phase angle, but the scattering angle. Actually, as in Sebastian's talk, the scattering angle, the same problem. The scattering angle is measured from the forward direction, so it is pi minus the solar phase angle there. Okay, just to remind us what the spectra may look like. If you take the Bas-de-Meo spectral classification system, the S complex has something like that as the spectrum from visible to near infrared. The C complex has less features. Maybe a curve like that would then describe a typical curve for a C complex asteroid. Then if you look at some components, let's say that we would really have a simple view of this. We would have olivine, pyroxene, carbon. What you would have then is basically the the olivine spectrum, the red one, a major absorption band near 1 micron, and then otherwise like that, there's huge hole here. Then the pyroxene, which would have 2 absorption bands, one in short word of 1 micron and one at the 2 micron regime, and then you would combine these to obtain actually some typical spectra. For example, the S-type spectra would then show 2 absorption bands there. And here in the bottom there would be carbon. If one would like to somehow darken this spectrum or neutralize, carbon would be a nice ingredient to darken and damp all the spectra. So no surprise there. Okay, just to remind us of what I showed yesterday for the basic photometric and polarimetric phenomena in the solar system for asteroids. We look at here the disk integrated phase curves for F, C, G, M, S, and E-type asteroids, where you can see potentially the evolution of an opposition effect there, actually getting sharper. For the S-type, you have the most pronounced nonlinear behavior in the magnitude scale, on the magnitude range, and then for E-types there is an abrupt effect. If you look at the polarization here, the most pronounced was for G-C types, almost 2% negative polarization, and then neutralization toward darker asteroids and toward brighter asteroids also. So that was this is something that is also imposing compositional constraints on the material, on the surfaces. Okay, so now let's get into the multiple scattering business. So here, this is how we want to think about this system basically. So basically one can cluster, what we see here is basically a size distribution of spherical objects packed together, densely packed, less densely packed together, and finally forming a regolith. And if you would zoom in here, you would see a size distribution of spherical grains. And what do we actually want to think about these models here? What are these objects? Are they precisely spherical, homogeneous, isotropic particles that could be treated with Mie scattering? No, not exactly like that. You can think of these as volumes that include some elementary scatterers. So there is diffuse scattering. There's multiple scattering interactions within each volume. But the overall geometry of the system would be something like this. So you could have you would build a regolith model stepwise, and it is actually easier to treat. At least it is easier to analyze the results from media that are finite. So what we will see today mostly is basically scattering results for spherical media of scatterers there, because then you again do a very simple phase angle analysis of this system. You don't need to worry about any incidence or emergence angles. You can concentrate on the angular dependence on one angle, the phase angle. Let's see how that evolves. So one could, for example, do the radiative transband coherent backscattering so that you could have a particulate medium of these kinds of volume elements, and then you could pack them together and have a fractional Brownian motion roughness on the surface. So this would be pretty good. This would be a realistic fractal model for a regolith rough interface there. Then one could actually do phenomenological fundamental scatterers, put them into these elements inside these spheres, and then do the treatment like that. Okay. This is kind of the picture a couple of years ago. So what can we do better? That sounds like hand waving still. There's not, if you talk about phenomenology, you think about, okay, maybe there are some degrees of freedom that are not fully actually taken into account. So what we try to do is something better today. And what we are showing today here is basically very fresh stuff, really unpublished basically. This was only published in one proceedings paper, the basic principles of this work. This is an electromagnetic theory symposium in August. This is the URSI, the Union of Radio Scientists, meeting every 3 years for the theory of electromagnetic problems, and we published this work, part of that work in those proceedings. So some written material exists on these methods. Earlier stuff was in the book, the Cambridge University Press Polarimetry of Stars and Planetary Systems. Then a comparison work between exact methods and this radiative transcoherent backscattering in APJ in 2012, a couple of years ago, and then before that there was a modeling paper on the lunar photometry that utilized an idea of these kinds of volume elements, and then the scattering of diffuse scattering within the elements. And there is a long history, and in fact I would like to point out that there is this medium actually derives from the work by Parviainen and Muinonen, and Hannu Parviainen is currently a postdoc here at the IAC and in the audience. It's nice to meet Hannu after many, many years actually, working on exoplanets now. Okay, so, and the story actually started from 2004 where the RTCP, Radiative Transcoherent Backscattering work was published in Waves in Random Medium. So let's move forward. Let's remind ourselves again, just a list what this problem is about, whether it be photometry, polarimetry or spectrometry. This multiple scattering would be a function of surface roughness, volume density of the particulate medium, size of small particles, shape, structure of small particles, refractive index, and all of these are distributions in reality. So there's nothing like one parameter per line here. So it is basically a distribution of everything in reality, in the physical reality there. Okay, so when we talk about multiple scattering, and I've already mentioned this word coherent backscattering a couple of times. So let's now define what we mean by coherent backscattering. Yeah, maybe it's a good time to actually draw something. So this is a simple idea basically of coherent backscatter. So if you have a regolith of particles and you actually go towards, let's say here, towards the backscattering, sequence-wise, order-wise, you propagate on some path, there is maybe some rough surface here. You can always go backward exactly the same way and then be registered at the backscattering direction so that you see that there is no difference in the optical path. Basically your interference for these two components in the wave are always constructive at backscattering. This is coherent backscattering. And okay, I have to warn you one interesting thing here. So I talk about coherent backscattering, I talk about incoherent fields in soon. Coherent backscattering is a phenomenon in the incoherent field. Sorry about that, the definition was really back in ages ago. It's kind of misleading, but really this is a phenomenon that will happen in the so-called incoherent field. We will see what that means in a second. Okay, so that's coherent backscattering. If you turn away from the backscattering direction, you will get destructive constructive interferences, and if you do configurational averaging, what is left is a backscattering peak basically. In other directions there are alterations of constructive and destructive, and they will be averaged to a lower mean intensity there. And then there is this basic polarization phenomenon in coherent backscattering, and that's a bit harder maybe to understand, but it's not too bad. This is almost any interferometry problem would have this kind of a plot where when you turn away from certain direction, you introduce a phase difference, and the phase difference here in this plot, for example, is the wave number times this distance d times sine alpha, and alpha is the same angle here. This is the phase angle from backscattering. So if you are in this plot and in the ZY plane, the observer is in the ZY plane, and you have this kind of interaction, you go here like that, or you go this way, you have a phase difference that is kd sine of alpha here. If you then have another plot, think about averaging over here. If you have off-plane scattering, you come from here, and then you scatter again to the ZY plane, which is the scattering plane here, and you come here here and you scatter again to the ZY, and you see that there is no phase difference. Now the question is, do these have any polarization signatures, these kinds of paths? And it turns out that this would be, if you have first order scattering positively polarized, like Rayleigh scattering, this is positively polarized perpendicular to the ZY plane in the x direction. And you see that the positive polarization will suffer from this phase difference, whereas this one, which is, again, remember, this is positively polarized in this case in the y direction. It scatters that way. There is no phase difference, and this is produces negative polarization without a phase difference. You average, you actually have different peak widths for negative and positive polarization, and the end result near backscattering is that the negative polarization is winning. So this is part of the explanation for what we see for the asteroids, for example here. So at least part of the explanation of these negative polarization branch. Remember from yesterday that the small particles from Olga Muñoz's laboratory measurements in Granada actually also show negative polarization near backscattering. That means that irregular small particles on average most probably also produce negative polarization. It's a slightly different mechanism and also contributes here. The thing is that what we want to do is to combine all this knowledge, put them into the same multiple scattering computation, and produce a sort of a solid view of how these would be then produced. Okay. So that's the idea in the negative polarization, and this was originated from Yuri Skuratov and myself. I wasn't aware of Yuri's work. There is even an earlier work for Yuri from a circular in '85, all this in Russian, but nevertheless now I think coherent backscattering has not gone away anywhere. I think it is strengthening all the time as an explanation for many of the opposition effects, if not all. It's playing a major role in all opposition effects in the solar system. Okay, and there is one more beautiful show of this. So any order of scattering, you can go to very, very high orders of scattering, and you always have the path that goes the other way, and this is producing the constructive interference and negative polarization also in higher orders. Okay, why is this significant? I mean, you can imagine that there are scatterings, so this comes and scatters there and scatters back and there and there and then goes somewhere. Why do they not destroy this picture? Why is this special? It turns out that if you do the statistical mechanics or physics of this problem, it turns out that only the radiative transfer type paths that go like the blue one here, through different scatterers in the system, and those that go through the same scatterers as the RT path, only these interaction diagrams actually survive when you do configurational averaging in the system. This is the statistics point of view of this problem. So if we would have completely random system, only these two interaction diagrams, and you can actually do them in the Feynman diagrams, only they would survive in the system. In real systems, we always have some non-random things there, of course, but the overall picture is that only the RT path and the coherent backscattering producing path are the relevant paths in a random system. Okay, let's see if I can convince you that this is the case. Okay, so there was a method that in fact was already, I'm missing that one graph that had the method here. Okay, so this radiative transfer coherent backscattering is a radiative transfer type method. So it is Monte Carlo radiative transfer with the polarization duly accounted for, and it is based on the so-called peel-off technique. So basically you do not collect rays into bins, you basically actually peel off the propagating intensity in the medium at any scattering process to prefixed directions, which means that we know exactly what the phasing is then. You can't do this for bin systems. If you collect 2 pins, you can't do the interferometry there. But when you define precise directions, you know precisely what the phase differences are. And that was the key thing that allowed for this kind of RTCP, because then you could do the reverse path and do the interference properly. So that was done in 2004, and part of what I'm going to show now is from an astrophysical journal paper from 2012, where we compare this approximate radiative transfer coherent backscattering method to exact computations. So this superposition T-matrix method is by Makowski and Mishenko. There's a code available for anybody on the web to look at these smaller systems exactly. And now we are in the happy position where these exact computations actually can reach sizes where it is meaningful to ask whether this approximate technique actually can produce the same result. It would be surprising. Okay, Sebastian was talking about radiative transfer in an atmosphere. Now what you will see is something like radiative transfer in 4 microns. It's the same equation, basically. Okay, so let's see what happens. And then on the way, we will later, after that comparison, go to this radiative transfer with rigorous transactions and see what we can do to improve the problems that we will also see here. Okay, so let's start with this plot. And I repeat again, we have the scattering matrix, which is basically the 4x4 matrix relating the incident Stokes vector to the scattered Stokes vector. And we are looking at the elements of this, and don't worry, it's essentially the same matrix. These are relative quantities as this P matrix. It is normalized in a slightly different way. Basically, we are just taking the elements of this and putting them here. And you see here in fact, the intensity distribution as a function of phase angle. This is P11 or S11 divided by S110. This would be the same. One example here, another example here. And then the polarization, again the same polarization thing here. It's now, in this case, it's the 2,1 element minus P21 divided by P11. And here we have the so-called linear and circular polarization ratios, which are often used as radar quantities. If you take an Arecibo radar and you look at the asteroid echoes in polarization, you talk about linear polarization and circular polarization ratios. And here the solid line is actually this approximation, this RTCP, and the dashed line is the exact computation. So this is encouraging now. We are talking about a system which is a 3% packing density on the left, 6% packing density on the right, and this is a spherical volume of particles with single particles having the size parameter 2 and refractive index in the single particles being 1.31. So ice particles in a loose spherical medium, and roughly 500 of those particles there in that medium. Okay, and the medium size is that roughly 4 microns that I mentioned. So this, in the visible, this would relate to 4 microns. Really microscopic system, and still, let's look at this a bit more, it is amazingly good in all respects in here. And this is for 0 to 30 degrees in phase angle, and it is even actually more convincing if you look at the entire 0 to 180 degrees, the full thing here. The only problem is at forward scattering, where we have the exact diffraction from the exact method, and this diffraction can be added to this RTCP if necessary. So it's not really a problem at all that there is a small uncovered domain in the forward scattering here. The overall agreement also speaks for the radiative transfer validity here. So the radiative transfer, coherent backscattering is a phenomenon near backscattering. Radiative transfer can cover the entire part, and you see that in fact it's amazingly good for the full range of phase angle. And we have a sparse system here, a few % packing density. Okay, so Timo Väisänen did some additional computations with more beautiful pictures also of this, and you see that the red one is the RTCP, and MSTM, multiple sphere T matrix, is the same as the exact STMM method, just another acronym, and the match is nice. Okay, so what is the problem? The problem is here, so you do not expect this to hold for close-packed media. So you go to packings that here we are talking about 30% packing density in the bottom. There is a huge difference in the polarization, for example. So this must fail. This kind of radiative transfer with far field input and interactions must fail. Radiative transfer is not made for close-packed media if you don't do any corrections there. So the deviations are clear, and the deviations also are appearing in the intensity here. Now this is now again in the scattering angle here, so backscattering is here. Okay, and now comes the new thing to do. So how to get rid of this, how to expand the radiative transfer, which is a very useful technique. How can we go to close-packed media here? And this is the time to actually now introduce some quite crucial things for this next step. And this has this introduction is an introduction of fields that are not necessarily like physical fields, but that they can be mathematically constructed. So coherent field. Imagine that you do the scattering problem. I think it makes sense to again draw something here. So let's assume that we define some volume, and let's start with the putting a single spherical particle here. And there is a plane wave coming. Okay. Then you have, if your particle, you have the origin, particle is away from the origin. You solve the problem, it's a mean scattering problem, but there is a phase because this has been shifted away from the origin. So now allow this single particle to actually appear in anywhere in the volume, but only keep the single particle there. And now do the coherent field, do the averaging of the field and not the square of the field. That means that basically the phases are washed out. So the mean scattering result will not be a mean scattering result. The coherent field is not the mean scattering result. It is actually something that is unique, that exists for whatever your position for the particle there. And what exists for any position is actually the diffraction peak. So what is left in the coherent field after this kind of single particle averaging is only the forward diffraction, and it actually comes down in the coherent field very quickly from the forward scattering. Okay, what is the incoherent field? Now the incoherent field is that you now have already computed the coherent field. The incoherent is that you now actually have a realization of particle here. You fix it in here and you subtract the coherent field from the field that the particle actually causes when it is positioned there. So that is the free space electromagnetic field minus the mean field. And this is now the actual incoherent scattering signal from the particle. And the theory says that in fact this is what one should utilize in close-packed media and actually in any radiative transfer computation, because this should be incoherent in that respect. Okay, so we go further. Instead of putting a single particle here, we want to put several particles. And we want to introduce a close packing here and take care of the close packing so that actually we solve this problem exactly for a number of particles. Then we can claim that, okay, we have taken into account the near field effects in the proximity of the particle, any particle, and this size has to be rather larger than the wavelength in question. So within a wavelength scale or larger domain, of an elementary volume, do the averaging so that you compute the coherent field and an incoherent field for a realistic, realization of a system of spherical particles. And what we wanted to do here is that we wanted to check whether we can actually remove the shortcomings of radiative transfer by utilizing the incoherent field here as the input for a radiative transfer or RTCP type approach, and even compute the scatterings, the orders of scattering rigorously between systems of spherical particles in a volume. Okay, let's see how we go. Well, what are we left with? We are, again, there's one freedom, one free parameter. It's actually the size of the volume here. So how do we know what to fix for the volume where we do this coherent incoherent field? It has to be the end result in a random medium should be invariant. I mean, it should be any volume that we choose to use in the wavelength scale or larger that we then utilize, and we should get the same result out of that. Of course, you know, in nature, if you do this measurement in a laboratory for a particulate medium, this will not have any dependence on any arbitrary volumes that are there. The result is what it is, and it should be invariant in our computations also here. So recipe, the first place is to revise this radiative transfer coherent backscattering input so that we actually use incoherent elementary scattering by this element. Okay. And then the next thing to do is to actually, this is from Timo Väisänen's master thesis, that these volumes of these particles actually talk to each other in a rigorous way, so that we have an exact solution for the scattering problem here for an incoming wave, and we know exactly what kind of scattering that actually produces. We take into account all near field effects when we go to the next volume element. So this element sees the exact scattered field from this element, and then we compute the scattering by that system based on the field that this was scattered. So the order of scattering comes this way, that you all the time maintain rigorous computation there. And the thing that is challenging is to generate in a Monte Carlo fashion the next volume element for the interaction. And there we use radiative transfer type exponential propagation. But the propagation extinction coefficient is coming from the incoherent fields. Okay, so let's have the mathematics. It's reasonably simple. Just to repeat, compute the coherent scattered field. An example was in 1995. For some reason, literature, there is no real other work on this that can be found in the literature where this would have been done. So we seem to be the first one to do that, in fact. So you take realizations of particle systems here, and you compute the mean of NR realizations, and you compute the mean of the scattered fields in the far field or anywhere basically. And the incoherent scattered field is then any single realization minus the mean here. And this is what we claim what is happening really in the particulate medium, close back particulate medium. And then we have the scattering coefficient and the absorption coefficient, and these are not computed from the free space scattered fields. They are computed from the incoherent scattered fields. You see that this has entered actually here, and we do that scattering coefficient in this way over the 4 pi here. And you will see in an example soon that these are really different quantities as compared to the free space input parameters. And that it is a substantial difference actually, and explains why there has been so much confusion about the existing other techniques for computing multiple scattering. Okay, again the same, just to repeat, and let's go to the preliminary results now. Okay, so how do we want to do this comparison now? So previously we looked at the RTCP versus this STMM exact computation. Now let's have a look at the what we can do with this exact computation. And with the exact computation, we could go up to 4,000 spherical particles in the system. Okay, so we know that this result is solid. That is coming from the Maxwell equations. We know it is. We can repeat this computation and get an average to whatever decimal place we want in principle, basically. You can go and reproduce that result from the Maxwell equation. And you can increase the size 1, 2, 20, 4080. And have the same example again. The single spheres in the system are small, size parameter 2, that means 0.2 microns in radius, roughly speaking. Then refractive index is that of ice. And let's forget about absorption in this comparison again. So the single scattering albedo is 1. And now let's take the RTCP with incoherent input. Do exactly this processing of the problem, do the exact computation for these volume elements, subtract the incoherent fields from there, and then average even the incoherent fields to obtain this input for the RTCP. Then do some violence also for the RTCP otherwise, but I'm not going to that. There has to be some other things also done. Nevertheless, let's see what happens. And then we have a comparison here. So if we did not do the incoherent, what would be the extinction mean free path? It would be, for a 15% packing density, it would be like 3 microns. This relates roughly to, in the visible, this would be 3 microns. Okay. And now let's look at the table. Don't need to read the text in the table, but let's look at the numbers and keep this in mind. Mean free path, 3 microns. And when we go to these mean free paths for the incoherent field, you see that there's a substantial difference, a factor of 3. So what this means is that the wave that is propagating in the particulate medium is not encountering like volume elements of scatterers so often as we would think from free space input parameters. So the mean free paths are substantially longer in the medium. That's a key result. That's also suggesting that maybe a far field approach like RTCP might actually work very well if you just put in the right parameters there. And what you see here is the extinction coefficient. Another thing to see here is that you increase, these are exact computation. So you increase the size of the system, and this is the size in size parameter range. So you go roughly to wavelength scale, 2 times wavelength scale, 2 microns, 6 microns roughly. And we are now making the comparison with these methods at 6 microns roughly for this last element. And if you look at the mean free paths or the extinction coefficients, you may see that, okay, there's something interesting happening in this range. The change is not so tremendous. So maybe there is a plateau somewhere here. So that it's rather stable as a result for any medium. You increase the size and you extract the incoherent coefficients, and they are not changing anymore that much. That suggests that, okay, now we're in the domain where we can actually accomplish something quite useful. And it is more substantially so for the 30% packing density. You see that here for the 20 and 200 particles in the element, this is essentially the same coefficient here. And the mean free path is essentially the same. So we are somewhere where things seem to be invariant here. That's excellent. Okay, because that is promising. You can then perhaps choose the 20 particle case and then utilize it in the computations and see what happens. Okay, so let's now look at some examples of how the incoherent scattering coefficients actually, incoherent scattering matrix elements look like. So the blue one here is the normal scattering matrix, 1, 1 element, and it is overlapping with the red one, which is the incoherent scattering matrix element. And it is exactly so that you have, with this averaging for the mean field, you have actually taken away the forward diffraction peak from here. So this is actually common knowledge that if you want to do a close-packed medium, you don't have diffraction, forward diffraction processes in that medium. You actually cut off the diffraction and use geometric optics as it is without the Fraunhofer diffraction. Now we see that in action in a rigorous way in this analysis. So We have even a dip in forward scattering for the incoherent scattering matrix. And it is quite flat, actually. So think about a system of, which is a very complex system of particle has a lot of structure. It is intuitively clear, actually, that you do not have so much maybe forward scattering in that diffuse component. The diffuse component is more like a back and forth bouncing there. There can be some wave that propagates through, perhaps, but it is not as much as the forward diffraction would indicate. So it is quite crucial to get rid of this diffraction pattern when you start doing close-packed media. And otherwise, if you go from the forward scattering direction to intermediate scattering angles towards backscattering, this is more or less, everything is more or less incoherent. That's another interesting thing. The coherent one, which is the dashed line, is coming down very steeply and it disappearing in the noise. It only is responsible for the diffraction. In the polarization, there are some, you don't need to worry about the polarization of this coherent. It's actually, there is not so much any power in there. But again, the polarization of the incoherent and free space signals is essentially the same. That's actually amazing why this is the case, but this is the true thing here. And then there is some depolarization now in the incoherent. And it is the same as also in the free space. So free space was that one that we were averaging, and then taking the average. Now we take average free space signals and compare them to the incoherent average, and they seem to be the same. Interesting. And it's the same story for all the rest of the elements. This was for the 15% packing density, and the story is more or less the same for the 30% packing density. And now we are in business because we can take this, and if you look at the, I can take you to a tour concerning the coherent backscattering and radiative transfer, photometry, polarimetry, but all the same, this is actually saying something very fundamental about the spectrometric applications, which are more massive in asteroid science, for example. So what does that mean for our basic tools for extracting physical information from the surface? That's quite intriguing. Okay, so now make a comparison. Put this into this RTCP code, which is on radiative transfer, coherent backscattering. Utilize incoherent input rather than the original me patterns for single particles. Okay, so what happens? And these are essentially the first comparisons where, let me see, I think the blue curve is the precise result for the 4,000 sphere incoherent scattering contribution that is exactly computed from the STMM method. And then which one was it now? I never remember now. I have to go back and see. So the red one is here the approximation type thing. So it is also here the approximation. So blue one is the correct exact result, and we have to compare to the red one. It's not so bad. This is this RTCP with changed input. This is, we do not have anymore any systematic polarization difference at the intermediate scattering angles, and the backscattering polarization is also not that bad. So as a first result, this was quite promising. And for the 30% packing density, we are in the game. It's not easy, it's not exactly the same, but we are in the right ballpark with this method now. So I think we actually have invented something useful. We have removed some systematics. There would be this RTCP result here with the free space input. Now we have replaced that with incoherent input, and we are actually here with the red. And the evolution is from a single particle in the volume to 20 particles in the volume, and it is actually improving the situation when you add particles into the volume and do the averaging there. So that's promising. One slide about the R2T2, which now is better than, definitely better than this RTCP with incoherent input, because this one takes into account the interactions in a rigorous way, and also there's no violence done for the method. It is a true method that computes the propagation paths, the RT type, CP type interaction diagrams, and adds them together with the assumption of exponential attenuation. And here you would see look at the red and green curves against the dashed curve. We are here, and here the match is quite good, except for the backscattering, because this R2T2 at this moment does not yet have the backscattering enhancement or the coherent backscattering factored in. Maybe next Monday we'll have it. We'll see how Timo manages to in his programming and how the supercomputer actually can manage these things. So now the key thing here was that the RT-CP is a desk. We can do this with the portable in 10 minutes. The rigorous computation takes hundreds of hours on a supercomputer. Okay, so I mean I'm tempted to actually try to develop this approximation into a tool that can be used on a portable. But it is nice to see that in fact with the rigorous approach it's approaching the right limits. And now what is the thing here? The exact method, we had this 4,000 spherical particles there. The limitation is around there. You can do maybe, what is the limit, 10,000 now, or perhaps even 100,000 spherical particles can be done with the exact methods if you really squeeze in, you really push for supercomputing and parallelization and everything. But this is too little for any regolith model. It still is not describing the actual problem that we have for asteroid surfaces. We have really huge systems compared to the wavelength. But with the approximate technique, like this RT-CP with incoherent input, it is no problem to go to 38 billion spheres in the system. I mean, you can go to essentially infinite systems after this all is set up properly. It is just to calibrate the system to convince everybody that in fact this is a way to do this problem properly, and then we can do these real life existing media in a proper way using the techniques here. So this one is that not a 1 meter particle or some, no, 10 to 4. That's actually not so large yet. It is still has huge number of spherical particles, and it's actually coming very quickly to large numbers of particles when you increase the volume. Okay, so let's see what that would mean, what imply for spectrometry then. Okay, so now we have a different system. This was a system of spherical particles in free space. So there was this close packing of small particles with 30%, but this is does not sound like a real system. So the real systems are particles that are like 50 micron, that are inhomogeneous inside, and actually then give support these random media within the actual particles. So how does this approach actually carry over to these real regolith particles and regolith particulate media then? Host materials. So what do we have? Okay, it seems clear that actually we can define a volume element inside the particle in very much the same way. Now everything is just in a host material, so here, and then we have an isolated volume of inhomogeneities, and we can compute this in a system and have a volume element very well defined for an internal medium. Okay, that's fine. Then we have to discuss the actual boundary between the large particle and then the medium inside. But this is something we can do with the geometric optics approximation in the first place. So we don't need to worry immediately whether there are any major effects between this kind of volume element and then a boundary somewhere that is basically the free space host material boundary. So this is possible to do. And there are even codes actually that can now be utilized for that purpose. So what we need to do for real life application is to replace the input that we would put from, let's say, a me code to this kind of radiative transfer with this incoherent computation. So you would average over a volume and take that and input that to a radiative transfer code. Okay, what does that mean? Let's take an example. Now, if you look at the situation where, okay, you have a, let's say that you have a large volume here, and you put something like a geometric optic-sized particle there. Imagine that you move the particle in the volume, and you make this phase averaging. So what is left? You are not changing the outcome at all. If you move that particle around and you do the ray tracing, the result is the same. So geometric optics actually is incoherent by its nature. So we are allowed to do a geometric optics computation and put that into for example, in a host material, put it back to the system. If it is wavelength scale, we need to do this incoherent coherent subtraction and then work out the input parameters. Fine, but this is all doable with existing methods, so no problem. So the recipe is there. Now let's go back to think about the Granada measurements for the single particles in the flow. So how would we actually utilize those particles now, these results? So these are free space results for single particles averaged over particle sizes, particle shapes, and so on. So how do we take that signal and then take it to our multiple scattering codes that mimic regoliths? There is a recipe there. We actually need to do it this way. We need to model the single particles and the scattering matrices that are measured with a realistic modeling effort for the single particles. Once we are happy with the match, so the single particle scattering modeling match against the laboratory measurements, we need to build these elements in the computer from the model particles, and then do the computation, solve this problem, and compute the incoherent parameters. And then we take the incoherent parameters and we put them into the multiple scattering codes. So there is a nice bridge from the laboratory measurements for single particles to actually input parameters to multiple scattering codes. And of course one can then go and do goniometric measurements for particulate samples and spectrometric measurements and see that actually they should match. Well, nobody has done this so far, so this is a thing to do. It's going to be interesting when we actually figure out the problems and successes on the way there. Okay, now let's go to some examples at the end now. So let's take a space weathering example, and just recall that this is not yet using any incoherent input. This is an overview of some existing old-fashioned way of doing the thing. And still the results are the same. Well, one may ask at the end, why are these results so good? So we will need to study that. So okay, so how would you do the space weathering effects in visible near-infrared spectroscopy? Okay, now if you believe we have a way to actually do the radiative transfer properly here. So we can talk about radiative transfer in densely packed media. It has a meaning. It's not illegal. It is looking good. So let's assume that we have nanophase iron inclusions in an outer layer like here. There is a 100 nanometer bar here. You see the nanophase iron in this transmission electron microscope image of an olivine grain. This is from Kohut et al. For the Chelyabinsk modeling, and see what we have. We can actually then have a controlled sample of pure olivine and olivine plus nanophase iron. Grain size 20 micrometers in diameter, and this is how the spectra would look in the near infrared in the visible to near infrared. So the nanophase iron causes this reddening of the spectrum. The spectra have been actually normalized at 1 at, is it 0.5 or 0.55 microns, so you are not looking at the absolute level change here in a proper way, but you see the tilt of the system here. Okay, weight fraction of nanophase iron here is 0.023% only actually, and the change is substantial. So you do this analysis now using this series rate ratio. And this is originally actually coming from work on Gaussian random particles, irregular particles actually presented by the Gaussian statistics, and then we have introduced actually multiple scattering, diffuse multiple scattering inside the particles. So you have reflection, refraction, diffuse scattering, and this is precisely now what we need for this kind of purpose. So in fact, there's a refraction then out, and finally there is a termination of ray tracing when the ray intensity actually goes to 0. So we have the tool. We can actually now look at we compute the nanophase iron input there, and utilize it in the diffuse scattering there. And why can we do that? The nice thing is that we have existing databases for olivine refractive index information across the entire wavelength range. This is the real part, from varying from 1.6 something to 1.63, and here we have the imaginary part, and we have the same for the iron. So we can actually do the entire simulation from first principles. No assumption of any, no hand waving at all, in fact. Very nice situation. This is where we would like to be with any material that is relevant for solar system surfaces, so to say. So we know everything. Just plug in and recall, now that we are doing the me computation here, something is interesting. We are not doing the incoherent one. We are doing the me. Single scattering albedo we can get from the me computations, and we know the weights. And what we want to do is we want to mimic an asteroid, so that means that we need to do this 2 times. We use the same code. We get an average asteroid spectrum here by averaging over Gaussian asteroid shapes, basically. So what to do first is to take model the single grain with and without these nanophase inclusions. So these are the spheres here. Spherical particles is the nanophase. We have particles with and without these inclusions. When we have these results available, the scattering matrix, we make the proper weighting, and we plug these in to the same code as input parameters. And now we use the code in such a way that these particles are actually in free space. So they're making actually an asteroid. All through the asteroid we have just small particles there actually packed. So this is a radiative transfer type thing done in using the same code for irregular objects and averaged. Okay, so this end result should be then the asteroid spectrum there. And this indeed actually produces in an acceptable way the measured signal. So measured pure olivine in here, nice match, and then measured olivine with nanophase iron, nice match. And then this is in preparation. So there is no publication about this either yet. Okay, you need to shape up in the publication domain. Okay, what does this mean? This is interesting. We get a nice result using me input parameters, and why would this not be in contradiction with what I was telling about the close packing system? It turns out that the nanophase iron actually is a very weak scatterer. So when you add nanophase iron, you basically add only an absorbing constituent, and it looks like this is mostly an absorption problem, so probably there is no problem coming from the usage of free space parameters, or I mean isolate parameters from isolated particles in the host material, not free space but host material in the surrounding medium. Okay, so good questions to actually ask. Okay, I'm running a bit late. Why did the measurements and modeling match? The free space here means host material single scattering, so you have a particle, and then this is the infinite medium of the host material, and the particle is there, and it's computed. Characteristics are input, and the match is nice. And how do we evolve from sparse media to dense media? These are open questions that we don't have the answer yet. Okay, so finally let's have one example more, and this is the Chelyabinsk meteorite spectrometry, and this is one thing, this is an intriguing shock metamorphism case where in fact you are looking at two pieces that have elemental compositions that are the same. So you have exactly the same amounts of various elements in this and in that, and yet there is a striking difference in the outlooks of the material. So you are really having a dark lithology and light lithology here. And yet, what is the explanation? Well, what I show you next may be a bit confusing, but don't worry, we will clarify this for next week. What you have for the bright sample is that your iron sulfide is in large sections. This is X-ray microtomography sectioning of these samples, basically. In the bright sample, you have these iron sulfides in large clumps, actually, in the matrix. In here, in the dark sample, these iron sulfides have been actually distributed amongst the olivine and pyroxene here, and they are producing much stronger absorption effects in the spectra. So very nice light scattering effect that how you have the iron in there actually affects the outcome of the spectrum and the outlooks of the system here. What is a bit strange here is that the voids are so clear in this dark sample, and there should be actually more voids in the bright sample, but these are different samples, so there's some confusion here. We'll clarify this soon. But the basic idea is that the iron sulfides are in different way in here, and what you see is by your own eyes is the difference, and you see the difference in the spectra also. Okay, so there's the input for the spectral modeling of the light-colored lithology, and then we have the modeling for the light, which is the match is more or less exact. Here the match is also very good for the dark. So we can do these computations with the series code, and let me underscore that there is a poster by Julia Martikainen downstairs about the Chelyabinsk. There's a poster about this R2T2 code by Timo Väisänen also downstairs, and then we can discuss these during the week. And then I go to the final part, which is the spectrometric inverse problem. That this is what I'm proposing, that we have a small project that we do more or less in a simulation fashion here. So 3 different samples: a pure olivine sample, an olivine sample with nanometer scale. This is like a space weathering example, iron particles. Then an olivine sample with submicron scale iron particles. And what we want to do here is that we can simulate with the series rate ratio the spectrum of an asteroid that is composed of such particles, basically. Then we can use the tool by Juris Kuratov and then extract the refractive index information from the spectra. This is an analytical model, simple model. It's like an inversion model precisely for simple analytical fast. And then there are very interesting questions now. They are both simulations. We do not do the so-called inverse crime. We generate the dataset with another code and invert the dataset with another code. So it will be an interesting check for the codes. Do they actually speak about the same refractive index or speak about the different refractive index? What does it mean if they differ? And how good is the analytical model, which is for the slab medium now? So we are basically describing an asteroid as a slab of a material and then doing this spectrum from the slab analytically. We are then generating the asteroid spectrum using this rate ratio that I explained a moment ago. Okay, so what is the challenge? The challenge is that we still need to generate the data for this project. So I promise we'll have tomorrow some data to distribute for the some observations. So we make the observations overnight. Let's see how we succeed. It requires quite a bit of work because of the wavelength coverage. You need to repeat the computation and have reasonable input parameters. So let's see what that produces. Okay, so things are in rather good shape for the numerical methods, and I think we are actually very close to having physically meaningful multiple scattering codes for the analysis of spectrometry, polarimetry, and photometry. So I'll stop here, and I'm over time, sorry. Thank you.
We have time for a pair of short questions, and then we will do a very short break, just to go to the bath, change the speaker, and continue, okay?
So for something like space weathering, you create the nanophase iron, but additionally you change the crystalline structure of the material. For something like olivine, you amorphize typically.
Yeah.
So is that something that the model can account for as well, or?
Well, yes, if you know the optical constants of that amorphized olivine, that's okay then, yeah. Basically, if you look at the, you can plug this into the generator, the series ray tracer that you generate the data, for example, but you can also do this in the Scurato model, that you basically can plug in differing
but you need
refractive index there.
You need the measured refractive index first.
That's right.
Okay.
And does that exist is another story then, yeah.
Now for the measured phase, for the backscattering peak in the measured phase function of the asteroid, I believe one of the contributors is also hiding of macroscopic shadows. Is this also somehow implicit in the model, or would this be kind of an add-on then?
Yeah, well, if you look at the, that's an excellent question, and I did not do that too much. We can go back to the modeling presentation. Oh, it's a long way, sorry. Here. Okay, so here, it actually is, if you do this computation, and build up the medium like that, you actually do have the mutual shadowing or shadow hiding of these spherical media. They actually impose shadows on each other. So it is actually included in there. But it's good that you pointed it out. That's the kind of a competing, or at least a significant contributor to the backscattering enhancement there. But now I personally feel that the coherent backscattering is actually more significant for most of the solar system objects at backscattering. You can actually quantify that statement after computation.
Okay, so this is
it is possible.
Quantitatively
yes,
in there
you
then
can
this way.
actually
Okay.
see what that is. Yes,
Thank
you can also measure the contribution from coherent backscattering and from the single scatterers actually to the polarization. You can get that at the end.
Okay, so we'll make a short break, no more than 5 minutes, please.